So let's start our topic. Can anyone tell what is CDC, if anyone knows a basic idea?
Hello. Am I audible?
Yeah, audible to me.
Like a signal which goes from one clock, like one clock to another clock domain. Like that signal, we call it as like the signal which crosses the clock domain.
Okay. So you're almost there. Clock
Okay.
domain crossing is generally we have generally what we have in our digital design is clock. So when you see any digital design, it works on a single clock or a multiple clock. So if in simpler words, we say CDC as when we are moving from one clock to another clock. So this clocks may be a synchronous clock or an asynchronous clock. So let me give you an example. So let's suppose this is domain A and this is domain B. And this domain A is working on clock A and this is working on clock B. So suppose this is a module. Let's suppose call it as a module A and this is be a module B. So each module, let's suppose, is having its own clock A and clock B. So what if this is my clock A and this is my clock B. And let's suppose I toggle something in the clock B. Let's suppose a signal was there. It was 1 and then at this POSH it became 0 and then it became 1. So we have two toggling over here. But while let's suppose this signal which was in clock domain B is being sampled by this clock, so we would capture this edge, correct? We would miss this falling edge and we would say that this will we would be again capturing this, so we would say that this signal has been like constantly 1. So we have missed a toggling of from 0 to 1. So this has to be taken proper care while we are traveling from one clock domain to another clock domain. So all of you have got the basic idea of clock domain crossing. Hello.
Yeah, yes.
Okay.
Hello, sir. Can you repeat one more time?
Okay. So there, let's suppose we are working on two module A and this module B, and each and every module works on a single clock, correct? So module B is, let's suppose, working on clock B and there is a signal, let's suppose A, which has to be transferred from this domain to this domain. Okay, so when you just see any compact hardware, so let's suppose this is my hardware. So it might be having some modules, right? This is module A, this is module B, and this might be talking to each other. What if this is working on clock A and clock B? And we have to transfer this data from this module to another this module. So let's suppose I have some clock. Clock A and one pulse, which is being toggled over here. And there is another clock. It's a faster, let's suppose some more. It's something like this. Okay, this is clock B. So can anybody tell what is the relation between clock A and clock B?
Clock B is 2 times of clock A.
Clock B is 2 times or 4 times?
4 times, 4 times.
4 times of clock A.
Okay, correct. So we can say that we are moving from a faster domain to a slow domain.
Yes.
Yeah.
Clock A is faster than the clock B.
Let's suppose clock A, let's suppose we are working on 100 megahertz. So clock B would be 25 megahertz, correct?
Yes.
Yes.
So let's suppose there is signal A, which is in clock domain A, and it is moving from domain. This is all of this is, and that signal is moving from clock domain A to clock domain B. Okay. So if we just sample that data at this posage, it would be 1, and this will go, this will go, this will go, and we would say that it is continuously 1, correct, in the domain B. But if we just see inside, if we just see the signal, there is a toggling of signal from 1 to 0 and then 0 to 1, correct? So we have missed this part of the data in the clock domain B, correct? So we have to make ensure that we have to be very much ensure that the data which has to be transferred from the clock domain B, clock domain A to clock domain B should be properly sampled, as well as it should be properly sent from the domain A to domain B. So this is what we say is clock domain crossing. So when we cross from one clock to another clock, how we send the data, it tells it is being guided by the CDC principles. So CDC tells how we would be sending our data from the clock domain A to clock domain B. Okay. Anyone having any doubt up to here?
No, sir.
So can we continue with different topics?
Yes, sir.
So now just give me a moment. So there are 2 types of clock present, which is one is a synchronous clock and the other is asynchronous clock. So let me tell you what's the difference between a synchronous clock and an asynchronous clock. or as you already know, do you know what are the clock sources which we use in our designs?
PLLs.
One is PLL, correct? Oscillators,
Crystal oscillators.
correct? Have you heard of VCO?
Yeah,
Yes.
sir.
Okay. Resonator,
Yes, sir.
so generally in our designs we use either PLL or either we use oscillator. Have anyone worked on FPGA?
Sir,
No, sir.
what question?
Yes, sir.
Have anyone worked on FPGA or any ASIC something, any flow?
Async flow.
Okay. So currently we work as currently in our designs we either we go for PLL or either we go for oscillator, but the output, as you know, the oscillator output is very resonating, so we need something to bandwidth this resonator output. So in our designs, let's suppose this is my design and these have 3 modules and clock is coming in through oscillator, and that from oscillator it is going to the PLL, and PLL generates the clock for different module, correct? So if the
Yes.
source of the clock is a single PLL, let's suppose this is the clock A and this is clock B, and the source of the both of the clocks is a single PLL, so we say that that type of clocks as synchronous clock. Let's suppose we have 100 megahertz clock and we have something like a 25 megahertz clock, but the source of both of the clock is same, so we say that both of the clocks are synchronous clocks.
Synchronous.
Or
Uh-huh.
or we can also define synchronous clocks as the clocks having constant phase difference. Let's suppose I have a clock and there is another clock, so if we just compare this, the phase difference over here is a 0. Sorry, I did. If we just see the phase difference at the posit only, we see that there is a phase difference of 0. So we say that the clocks are the synchronous clock. Okay. So talking about the synchronous clock, if let's suppose that the source, if the source of the clocks are from a single PLL or a single clock source, we say that the clocks are the synchronous clock, or either they should have a common phase difference. Okay, so a question for you all. Let's suppose I have 100 megahertz clock and the other clock is 100 by 3. So are these two clocks synchronous to each other?
No.
Can you say why?
Sir, I think we cannot comment on it because we don't know the phase difference.
Okay, so we can compare the phase difference by comparing the posage of the clock. So let's suppose we are working on any posage. Take any posage. So let's suppose I'm working on this posage and compare this posage. If this aligns, we can say that they are in the 0 phase difference, or either they are having a 360 phase difference. Okay. So can we tell what if 100 megahertz and 100 by 3 are synchronous clock or not? Hello.
I think they are a non-synchronous clock because the phase is 100 by 3 means it will be 33.33. So the phase difference, there will be a phase difference, I think so. So they are considered as a async clocks.
Yeah, correct. But,
and I have one more doubt, sir.
yeah, tell me.
If the source for this 100 megahertz and 33.3 megahertz is one, means if they both have the same source, they can be say as synchronous.
No, actually that only I was there to correct that. We have to see the source should be same and the phase difference also should be a constant.
Okay.
Okay. So these are the two. I correct my statement. Actually, the source should be the same, and another thing that they should have a common phase difference.
Okay.
So
Thank you.
So we
sir,
can say that.
Excuse me, sir. So this one should be synchronous, right?
100 and 100 by 3.
Yeah.
Okay. Anyone else? That anyone can guess, like it's not a big deal that if you say anything wrong.
Sir, it is asynchronous. Both are asynchronous, sir, because reading and writing of both the clocks are different. So both are not happening at the same time.
Okay. Okay. One is 100 and other is 100 by 3. Okay. So can you say that 100 by 3 exactly is 33.33? We can't say that, correct? This can be 33.367, or it can be 33.3335, or it can either go 3.33333. Depends upon the floating point section of any core. So it will totally depend on the floating point. Do anybody know what exactly sits inside the CPU core? Any rough idea? Okay. So if you just see any CPU, we have L2.
So like this, we have a different.
We have L2, FP, load storage, floating point, DE, FP, load storage, accumulator. So these are the major blocks of any CPU. But so there is a block called floating point inside every CPU. So that,
Okay, sir.
So that tells us what would be the exact value of 100 by 3. Okay. So every time when we have 100, and sometimes it can be 33.36, 33.335, or 33.333. We can't say that. So we say that there is the phase difference between these clocks is not constant. So we treat them as an asynchronous clock. Okay.
Yes, sir.
Okay, so one more question. So I have one clock as 100 megahertz and another clock is 25 megahertz. This is 25. So are these two clocks synchronous?
Only if the source is the same, sir. Because
Correct.
phase is matching. Only if the source is also same, then it can be synchronous.
Correct. So by just seeing the signals, we can't say that these clocks are synchronous clock. We have also to see the source. Okay. So let's suppose a real case scenario. This is SOC 1. You all understand SOC, correct? You all understand what is the meaning of SOC?
No,
System
sir.
on chip.
Okay.
No.
Okay. When you just see, have you all seen any PCB board that is in green color?
Yes, sir. I see.
So that green color has some chips, correct? Black chips.
Yeah.
Black chips.
Yes.
Bumps, sir?
No, not bumps.
Okay. Okay, black color thing, hard one.
Yeah, ICs. We call it in a layman's term, we say it ICs.
Yeah,
Okay.
I see.
Yeah, sir. Yes, sir.
Yeah. So just give me a moment. Yeah. So inside IC we have some SOC, system on chip. Okay. So let's suppose I give you a simple example, a very simple example. Have you any, when you just see a CPU comprises of many core, correct? Have you all understand what is the meaning of core?
Yes.
Yes, sir.
CPU core i3, i5, Ryzen 5, Ryzen
Yes, sir.
7.
Yeah.
Yeah. So each core has some peripheral memory attached with it. Okay. Okay. Just give me. Otherwise, I will give you an example of any SOC from that. Okay, just leave it. Okay. Forget this one. We have some module A, module B, and a single clock source is coming through a physical wire this is clock A, and this is clock B. So can we say this? This is a single PLL. Can we say this clock A and clock B is synchronous to each other? This is another chip and this is another chip. So
So
can
we
we
have
say,
to see the same
yeah, but
because the source is
Frequency.
both, let's suppose both of the frequencies 25 megahertz only.
Yes, sir.
So can we say that both of the clocks are a synchronous clock?
Yes.
Okay.
Yes, sir.
Okay. But did you see its phase? Like let's suppose I have one clock 25 megahertz
the waveform.
and another clock is 25 megahertz only.
If they are same source, they should start at same point, no, sir. Unless they have any delay like that.
Yeah, you are correct with it, but that definition comes when we don't have any jitter values, correct? The clock can have some jitter values.
Yes. Okay.
So you can't say from just like seeing the architecture, we can't say that it's a synchronous clock or a asynchronous clock. No, we can say, we can guess that it should be a synchronous clock, but you can only rely when you see the waveforms. Okay, now all you have got what the basic synchronous clock is.
Sir, if we are including the jitter or skew some effect to the cycle, then it will be always like synchronous because some delay or some kind of effect should be seen in that in practical sense.
Yeah, so that's what I'm saying, that this can be a asynchronous clock if they are on a different die. No, you would not understand. I would say different chips, because chips is a layman language. You not understand what die is. Okay, so so all of you understood what is. So all of you understood what is synchronous and sorry, asynchronous clock. Sorry, synchronous clock. Hello.
Yes.
Yes.
Okay. So let's move to another topic. Are you able to see the PPT?
No, sir.
It is showing some blank screen. Now we can see.
Okay. So consider. So I think. So I think CDC is not a good topic like for you all. Let's suppose. Okay. So all of you understand these blocks. Like if the clock is from some same source, just see they have a constant phase difference. If they have a constant phase difference, we would say synchronous clock. Otherwise, this will go into asynchronous clock category. Okay. So why do we need clock domain crossing? So issues which we face during a clock domain crossing are, first of all, let's suppose you all understand what is metastability.
Yes, sir.
What do you mean by metastability? Can anyone just give a vague idea?
Metastability means the data is undetermined.
Okay. And why does that metastability stages comes in any flop?
When the two clock transition are very close to each other, then the metastability state occur, and it will lead to the non-deterministic value of output.
Okay. So anyone knows about setup time and hold time?
Yeah.
Yes, sir.
Okay. Can you just give me an idea about setup time and hold time?
The setup time is the minimum amount of time for which input must be stable before the active age of clock.
Okay.
And hold time is the minimum amount of time for which input must be stable after the active age of clock.
And why do we need that setup time and hold time?
Basically, for a proper communication between launcher and capture flip-flop, our input must be arrived at a proper time. It should not arrive too early or too late. So that's why we required setup time and hold time for hold the input data, and in
Basically, for proper reception of data, these constraints are required so that metastability don't occur.
Yeah, but exactly I mean to have you gone, have anyone gone inside the flop? What is a basic flop is? Okay. Setup time is the minimum. Okay. Okay. Let's go to a very basic. A flop is made of back-to-back master and slave latch. This all you know?
Yes.
Okay. 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 So okay. So let's suppose I have one flop. Okay, leave it. It will not help you. Okay. Okay. So let's have a actually I'm not CDC. I think it's not the topic for you all. Actually, I think CDC is. I think I would have presented. Achha, let's start with latch. What are the basic differences between a latch and a flop?
The double triggered and edge trigger.
Okay. Anything more?
Latch doesn't contain clock, and in flip-flop we apply clock signal.
Okay. What about area power?
Latch will have more require more power and more area because it is a level edge trigger. The signal should be active.
Bro, I told you that flop is made from back-to-back latches, if you just remember.
Latch require less area and less power, because
yeah, latch requires less, because if you just see any flop, This is a latch circuit. Okay, sorry, flop circuit. This is a latch circuit. So you can already guess who requires more area and which requires more power. So now you can say that flop requires more power
Or more area.
and more area. Correct?
Yes. Yes.
Yeah. But can anybody say why we don't use latch in our, why do we avoid latch in our circuits? Why do we use only flops? Why everyone says that avoid latch in your design, use flops in your design?
Basically, latch
Mainly it is on the
insert noise.
The occurrence of the event is taking a longer way, whereas in the edge it is taking a instant way to execute the.
But we let's suppose we have that benefit, correct? Like let's suppose if I am having my signals, I want to toggle it twice. I can toggle it twice in this latch. But that is not applicable flop. So, but still, you go for flop only. Why?
Because of the clock signal, using the clock signal, we can control it. When we are not using it, we are not applying clock. But in latch, once the input is there, the output goes on coming out. So I think because of the control issue.
Okay. So we can use clock
Also,
gating
many
over
kind
there.
of memory elements would be occurring into the
Then
system.
both are
rather than-
like we can't say both are the memory elements only. Latch is also a memory element, and flip flop is also a memory element. And someone told that we can use that a clock is something S triggered, so we can use that the flop. So we can do the clock gating over there. Clock gating is some other technique. We will not go for clock gating. So look, as you already know, latch is a level sensitive, correct? So in our digital circuit, we can have a glitch at the level also, correct? And that glitch can pass on. So that's why we avoid latches in our design. But do you know, we somewhere uses latches also in our design.
Hello, sir. What is
Hello?
glitch? What is glitch in here?
Okay. Okay. Let's suppose this is A, and generally this A comes and there is another A, okay? But that A comes, this A comes through a buffer, then goes another buffer. So it comes here, again A, okay? So let's suppose my A was this. So this A would be a little shifted A, correct? And we are ending this. So when we will end this, we will get something like this, correct? Let's suppose so my output would be something like this. We say as A dash output. So these two waves, which are unwanted waves, which are being generated, we say them as the glitch. Okay.
Yes, sir. Okay.
So the unwanted signals which you don't want in our digital circuit, we say them as a glitch. So this glitch, ideally the output should be 0. Sorry, not 0. It should be something like this. Sorry. So ideally the output should be like this, but the output is something like this. So these are the two generated signals which we don't want. So we see them as a glitch, the unwanted signals. And this can propagate when we having a level triggered circuit. But can anyone say, but why do, like, we have invented latch, correct? We have flop also. But in our designs, we use latches also. Can anyone say where we use latch?
Pipelining.
Pipelining, you are somewhat correct, but exactly not correct.
Time borrowing.
Yeah, time borrowing is a concept. Good one. Okay, please do. Please, all of you know what is clock gating, what is lookup latches, what is time borrowing. Somewhere we need time sequencing in data path. So these are the general uses of latches which we use in our digital circuit. Everyone knows Verilog over here?
No, sir.
Okay. So actually, I'm not taking CDC. I'm just revising all your concepts of digital so that you may. So when you just go to any interview, it might be good for you. All of you know what is reset?
Yes, sir.
So reset is of two types, correct? Async reset and sync reset.
Yes.
Correct. So why do we so general in phone, what we have, like when you press any reset button, it's a asynchronous reset or a synchronous reset? Generally, when you press any button of any device, it's a asynchronous reset. Let's suppose this is a device A and this reset is going to this device, it's a asynchronous reset. And inside in our device, that asynchronous is converted into synchronous reset and it is further used in our devices. Okay.
Okay, sir.
Okay, so do you know pulse to level circuits? How would you convert a pulse to a level?
Through
some RC network, charging the capacitor or something.
From I am talking about that is from analog part. What about digital part? Okay. So first of all, we
By
need
using
whenever
monostable circuit, we can generate.
we can use IC 555 timer IC, but that's like when you go to any digital interview, they will not say this all. They will just ask what would be a simple digital circuit. Correct. So first of all, whenever you get an positive edge, that data has to be latched. Correct. So first of all, we need a mux. Let's suppose my signal is 1. So that one output goes over here, and then so what do you all think? This will work? So whenever my signal is 1, it is the previous value of this flop would be 0, correct? Hello.
Yes, sir.
So this 0 will come here, come here, and up to here it would be 0, and from here it will become 1, correct? So this
Yes,
1
yes.
will get passed on to this values. So we have 1 over here. Now, when the signal is 0, this is 0. Now this, after it has become 1, when it has become 1, now it will again pass on, and now this 1, and this is 0, and this 1 will pass on, and we have a proper level to a pulse converter.
Sir, is there a need of that D flip-flop? Can we directly give the output of the mux as the feedback?
Okay, you are saying something. Look, this is just a memory element. If we just remove this, let's try with this. If yes. So you are saying this. So at this previously it was 0. So we can't judge what is the output over here. Let's suppose the output is 0. So it is coming back over here. Okay, 0. And this is 1. This 1, it has reached 1. But at the same time, this 1 will not be stored anywhere over here. Like there should be some memory element inside this path. Otherwise, it will just give this 1, and at the second moment of time, this 1 will just die off. You would not be able to see it 1. So we would be needing any memory element in this path so that that 1 is being stored at that memory element. Okay. Hello.
Okay, sir.
So any interview topic which you all want to discuss?
Time borrowing.
Okay. So then let's close this session. All the best.
Hello, sir.
Sir,
So why setup and hold time are required?
Okay. Okay, for that I have to draw one figure. when you just go inside any flop, this is all present inside a flop. Okay, so let's suppose my signal D is there, and some signal D has changed. So first of all, when you consider any flop, and there is a master and a slave. So first of all, inside every flop, we have a latch, slave latch, and a master latch. So first of all, whenever there is a toggling at the D, so this data will go over here, and there's a clock. Let me explain you through the clock. So okay, so clock is at this moment of time, the clock is 0. So it will, so this gate will be open, okay, and my data will travel up to here. So I would say when the clock is 0, my data is being stored in this slave configuration. Okay, so this is the minimum amount of time. This is the minimum amount of time we need so that our data is being captured. Hello, Akhil, can you please mute? Yeah. So our data is being captured by this latch flop. Sorry, latch. So sorry. So that this data is being captured by this latch, the slave latch. So this, so the traveling of the data from here to here needs some time, correct? If let's suppose in this moment of time, my data is not being stable, my data is not stable, so I would vary my data from here to here, so that the previous data is not being stored. So how would the next data will be but stored? So slave latch doesn't get an idea which data has to be stored, either this data or either this data. So slave latch needs some time to store the data. So that particular moment of time is our setup time. You all got it? What is setup time is? Why we need setup time?
Yes.
Okay. And similarly for hold time, whenever this clock becomes whenever this clock becomes 1, whenever this clock becomes 1 in, so this gate opens. So some and the previous data which is being stored, this yellow one, is being transferred to the outside world. So, and this all gate opens when the clock is 1. So when the data is being transferred to the outer world, we need some time to that the data should be properly transferred to the outer world. Otherwise, the data would be would be not properly transferred. So that moment of time is the hold time after the clock becomes 1. Okay.
Sir, can you repeat?
So whenever this the clock becomes 1, this gate is opened. Okay.
That gate closes, right?
No, that will become, oh sorry, this gate will become, sorry, this gate will get closed. So that gate closure needs some times. So in that moment of time, let's suppose the gate takes sometime 5 millisecond, 5 nanosecond. So up to 5 nanosecond, we should not transfer data from here to here. So that moment of time is the hold time.
Okay, so hold time only depends on that transmission gate, right?
Yeah.
Just that one.
Hello. Sir, in the interview, if someone asks question, then how can tell them instantly, because we does not have time to draw this circuit.
Yeah, you can just say that setup time is the minimum amount of time for which the data should be stable before any clock edge, so that it should not go to any metastability. I've just drawn this for your explanation.
But they ask why this required setup and hold time, where they come, then what we answer.
So in that moment, you just have to draw this diagram. Because they will ask, they will go inside the deep. Why do we need exact, why do we need setup time?
Yeah.
Any more doubt which you all have?
Sir, can you explain clock gating?
Clock gating I can explain, but like for you it's okay, but for other students it would be a little tough.
Sir,
Yeah, but I can give you a very vague idea. Clock gating is used for power saving. For power saving, we generally need 4 techniques. One is our voltage, one is clock gating, another is power gating, another is power frequency, voltage crossings, and the last one is, I think, the voltage, different voltages crossing. So generally we go for power gating and clock gating. Just a very big idea. Which yeah, any more doubt?
Sir, what is lookup latch?
Lookup latches, you can ping me personally if you want in the group. I can explain you.
Okay, sir.
sir,
Yeah, tell me.
hello. Sir, I'm a beginner as I will be starting MTech from the next month. So, sir, from where to start means in VLSI, what to learn and how to proceed? Can you please guide me?
I would say first is
you have to start from digital electronics, then RTL coding if you want to go on front end side, or you can go to physical design side also. Some different profiles are there in VLSI, so you have to know about those profiles first. But digital electronics is basic.